turn to page 44 in our books. Now this is the graph that we had from the equation that we had from before that we had already factored, and now we're trying to graph it. And we had 3 x-intercepts, and we found out that we went through this x-intercept, we went through this x-intercept, but this one we didn't. And this one we bounced off of. And we're going to use that language to describe it. We bounced off that one and then went back down. Now, what's special about the bounce when we look at the factored form of the equation compared to the other x-intercepts? There's 2 of them. So we could write this equation as x plus 2, x minus 2, and x plus 1 squared. And we're going to find out that any time that you have one of your x-intercepts squared, it's going to bounce off of there. So the next thing you're going to wonder about is what would happen if it was cubed, or if it was to the power 4, or the power 5, or power 6, or power 7. What's going to happen to the graph? And so on the side page of 44, because you got some space in the column there, we're going to make the following notes. If you have an even multiplicity, in other words, if you have one of your factors either squared or to the power 4 or to the power 6, it'll always bounce. It's not a proper mathematical term, so I'll put it in quotation marks. I don't know. Yeah, it doesn't. I'm looking at the textbook if it had any proper terminology, but it just says it touches but doesn't go through. So, and if you have an odd multiplicity, the graph will go through the x-intercept. But something interesting happens. If the multiplicity is a 1, so if you just have 1, it just goes straight through. But if the multiplicity is 3, 5, 7, anything higher than that, then when it hits your x-intercept, it bends and then goes through. And you've seen this. Oh, that's a throt. There we go. It bends and then goes through. And you've seen this before, because one of your parent functions has a multiplicity of 3. You just never thought of it that way. Y equals x cubed. So if we think of y equals x cubed, I mean, technically, you could write that as x plus 0 times x plus 0 times x plus 0. Or x plus 0 all cubed. Now, we never write it that way, but that's basically what it is. And it has 3 factors that all have 0 as an x-intercept. But when we graph it, it goes through, but the graph bends at our x-intercept. And an x to the 5 graph has a bigger bend. And an x to the 7 graph, x to the 5, x to the 7, x cubed, they all look similar. This would be an x to the 5 graph. And an x to the 7 graph would have a sharper bend going through it. But they would all have a bend at your x-intercept. So what we're going to find is we know how things act as end behaviors. We've talked about the end behavior for an even function acting like a parabola, either up or down, and the end behavior of an odd degree function acting like a line with either a positive or negative slope. Now we found our x-intercepts. And now if any of our x-intercepts happen more than once, we know that it's either going to bounce, go straight through, or bend when it gets there. So now we can look at example 3. And we can sketch these graphs. The nice thing about these graphs is they're already pre-factored for us. So that saves us some time. So the hardest questions would be, it's given to us completely, you have to factor it, and then you have to apply your knowledge of graphing. But for these ones, they're already factored. So when we go to graph them, we're going to start by labeling all of our intercepts. That means x-intercepts and y-intercepts. Our x-intercepts are 2 and -1. Our y-intercept, when you plug in 0 for x, you'll get 1 to the power of 4 times by a -2. Our y-intercept will be a -2. Now, when it's given to us in factored form, we have to think, what degree is this? If you multiplied this all out, what would be the highest power of x you would get? And we're not going to multiply the whole thing out because that would waste our time. We're going to get an x to the 5. Can you see that in the first one you would get an x to the 4, and in the second one you just have an x? And if you multiplied an x to the 4 by an x, you would get an x to the 5. And it would be a positive x to the 5 graph. Again, if we just look at our x's, here you'd get a positive x to the 4, here you'd get a positive x, so you'd get a positive x to the 5 graph. That means that this graph acts like a line. Its end behavior, it's going to start in the bottom left and end in the top right. Of our factors, do we have, which ones are bounces? -1 will be a bounce, and what will happen at 2? Will it bend? It just goes straight through. So if we know that we have to start down here. We know this one is a bounce, and this one is a straight through, and this would be a sketch of our graph. Okay? And for now, this is all that we know. Now, this is an x to the 5 graph. There might have been in here another little thing like that. Who knows? But you don't have to show that. All we have to do is show that we know the end behavior, that we know what happens at our x-intercepts, either bounces or bends or straight through, and that it goes through your x-intercepts and your y-intercepts. So there we have our sketch of our graph. If you type it into your calculator, you'll find out other information. So after you've done your sketch, you can type this into your calculator, and you can find out, now, does it go way down further here than my graph did? It's possible that it does. But we don't know that from just sketching, and that's okay. So for part B, same kind of idea. We know that we have x-intercepts at -1 and 3. What's our y-intercept going to be? +3. If we multiply that all out, what power would we get for g of x? It'll be an x to the 4. Will it be a positive x to the 4 or a negative x to the 4? It'll be negative. So one thing I like to do is I like to just imagine the x's above each of the brackets. So For x plus 1 cubed, that would produce an x cubed. And for x minus 3, that one has an x. And both of those would be positive, but there is a negative out in front. So if you multiplied all of those together, we are going to get a negative x to the 4 graph. And with that negative x to the 4 graph, we know that it acts like a negative parabola, so it's going to start in the bottom left and end in the bottom right. So now we can go to our graph. What's going to happen at -1? A bend. What's going to happen at 3? Straight through. So we come up to -1, bend, and straight through. Now, when you're graphing these things with the bend and going through the points, you want your pen sort of to flow. So I know it's going to be natural when you hit a point like the 3, you're going to want to bend it back down. And it's just a natural feeling. I hit a point, that's my highest point, so I should stop there and make that my maximum and then come down. But you just sort of want to graph it. It'll be more accurate if you sort of just let it flow. So when I was graphing here and trying to make it flow, when I got to the 3, it felt like I shouldn't go down yet, that I should just keep sort of looping up and make it smooth to come down there. And that'll be a more accurate. Now, it may go way higher than that when you graph it on your graphing calculator. But as far as a sketch goes, this is fine. Because we are dealing with powers to the 4, right? So if you plugged in 2 to the power 4 is already at 16, so we could get some very big numbers in here. So the extent of our graphing, if we review everything we've done so far, we started with table of values. And you can get a bunch of points from table of values. And if you wanted to add more points to make your graph more accurate than we had right here, we could add some things with our table of values. So we could go x and y. Well, I don't know where 1 is, so I could type that in, plug it in. What would I get? I don't know where 2 goes, so I could plug that in and find out where that would be. And my graph would be more accurate. Okay? Of course, some of these values, depending on how big the powers are, you'd need your calculator anyways. And if you have your calculator, you may as well use the graphing function on your calculator to check. Did you know that after you graph something on your calculator, that above the graph button it says table? You ever seen that? So let's just type in this last one. What was it? Negative x plus 1 cubed bracket x plus 1 to the power of 3 times by bracket x minus 3 So we see the bend in the graph. Yeah, it did go way higher than what we drew it. And it goes through 3. But above your graph button, if you go second graph is table, and it makes a table of values for you. So if you have your calculator and want to make a table of values quickly, this is an awesome way of doing it, because it tells us that at 1, this point here should have been at 16. And at 2, this point, obviously my graph is very accurate, is at 27. So my scale is perfect here, right? Because this apparently is 3 up here, and this is another 13 up to that point. Perfect. So if I drew it more accurately, I guess my graph would have had to go through this point, up through there, and then, whoa. Yeah, something like that. That would have been a more accurate graph. But as far as our sketching goes, this is going to be good enough. But it's nice to see that you have that access on your graphing calculator, that you can get all of those values quickly. Like, so if you were really curious what happens at 10, you now know it's at negative 9,317. Yes. So, questions to do for practice. 9, 10, 11, 12,